Hello. I never really know how to start these, so I'll just say hello. Today we are proving that the sum of cubes of the first n positive integers is equal to n times n+1 divided by 2. I don't know why I wrote n squared. This is from Rosen, Discrete Mathematics and its Application, Chapter 5.1, and this is question 4. The 7th edition is question 4, so if you're using a different edition, this could be another question, 5, 6, 7, whatever. For me, it's 4. All right, so the sum of cubes. So in other words, 1 cubed plus 2 cubed plus 3 cubed plus ... all the way up to n cubed is equal to the quantity n times n+1 divided by 2 squared. And we want to prove this by induction on n. So here's the proof. And we'll write by induction. Okay, so we begin this with the base case. The base case is just the first integer in this sum on the left is 1. And then we're going to replace n on the right-hand side with 1 and see if the left-hand side and the right-hand side are equal, which means the base case holds. So on the left-hand side, we can just assume that the first term is the n equals 1 term, which is 1. Or if you want to look at this form here of n cubed, m cubed is 1 cubed is 1. So the left-hand side is 1. If we were to do n equals 2, we would look at the first two terms, right? We would look at 1 cubed plus 2 cubed, and we would be looking at the left-hand side equaling 9. So if you want to look at some other cases of n in the base case, generally we just check the first, but if you wanted to see just intuitively what's happening, you would always think of the nth term as being the sum up to that. So if n is 5, that means it's the first 5 integers cubed and summed. But again, you only need to really show the first case in n equals 1. So let's look at n+1 divided by 2 squared. And we're going to replace n here with 1 and see if it equals 1. If it doesn't equal 1, well, then we have a problem. But so 2 divided by 2 is 1. 1 squared is 1. So that's the right-hand side. So the base case holds. The left-hand side and the right-hand side are the same. So we can proceed to the inductive step. The inductive step is where we first establish our induction hypothesis. Most discrete mathematics classes or number theory classes, you will replace your n with some other variable. It's just so we can differentiate essentially our induction hypothesis, the assumption, with the thing we're trying to prove up to n. In other words, k will be some fixed integer, and then k+1, the next case will be what we're trying to prove. All right, so we're going to assume that 1 cubed plus 2 cubed plus 3 cubed ... to k cubed is equal to k+1 divided by 2 squared. So we're going to assume this is true. And again, this is our induction hypothesis. I'm going to put a little IH here. Now, in our proof, and this will be algebraic, in our algebra, we will use the induction hypothesis. I've said this in other videos. If you don't use your induction hypothesis, you probably made some assumptions you shouldn't have, or possibly you've done something wrong and just happened to arrive at the same possible conclusion that you originated with or wanted to get to. Now, let's look at what we're trying to prove. So I'm going to write, we want to show, as a reminder, and what we want to show is the k+1 case, right? Some books will do p k+1, and then the induction hypothesis, the pk, that means that the base case is p1. Depends on your professor, I suppose. I don't really think it's that important, but I know why I'm writing squares and cubes. So then what we want to show is a k+1 case holds. In other words, when I add a term, is that equal? And I'm going to replace up here in our induction hypothesis, we have these k's, k+1. I'm going to replace the k's themselves with k+1. So the first k becomes k+1, and the second k is k+1 plus 1 divided by 2 squared. So this is what we want to show. I'm going to put a question mark here because they're not necessarily equal. That's what we want to show. Let's clean up this right-hand side a little, just so we're clear what we're trying to get to. k+1 plus 1 is k+2 divided by 2 squared. All right, so that's our task here, is to show that the left-hand side and the right-hand side are the same. But these kind of induction proofs where there's a summation and then a closed form, most often you're going to start with the summation side. So in this case, this is our left-hand side. We're going to take the left-hand side, use our induction hypothesis, manipulate it algebraically to show that it's equal to the right-hand side. What I like to do first is I like to rewrite the left-hand side. Just so it's clear what I'm doing. So the first thing I'm going to show you here is that we're going to group the summation to all the way up to the kth term. Now, this might seem a little trivial because I'm just adding parentheses, but this allows us to see a little more clearly that 1 cube plus 2 cube plus 3 cube all the way up to k cube, that's our induction hypothesis. That was the assumption we made. And we said that this summation here is equal to k plus 1 divided by 2 squared. So I'm going to replace it with that because that's our assumption. And then we have this k+1 cube term on the right here. I'm going to make a note to the side and say this is by the induction hypothesis. By IH. That's why I can replace that summation to k. Okay, so we are off. So now we have a sum. So well, first, maybe let's look at this a little differently. Let's look at the top and the bottom of this fraction as this. And so 2 squared would be 4. On the right-hand side, that's a fraction over 1. Now, if I want to add these, I have to get like terms. So that means I'm going to multiply the right-hand side by 4 over 4, which will give us k plus 1 squared plus 4 k plus 1 cubed divided by 4. Okay, so again, some algebra. This k times k plus 1 squared, I did a video on some college algebra topics. One of them was exponents. So if you remember your exponents, if I have a times b squared, I can write these as a squared b squared. So I'll say this is a rule. If you need to review my videos really thorough, it goes over all the exponent rules. So check that out. So that means I'm going to use this rule and write the left-hand term as k squared times k plus 1 squared. And then we're going to have this by 4. The reason I wrote it like that is so when we factor out the k plus 1, we're going to take out a k plus 1 squared, and we're going to take out 1/4. So here we're going to factor out k plus 1 squared from each term and 1/4 from each term. So k plus 1 squared divided by 4. And then what are we left with? On top, we are left with a k squared, and k plus 1 squared was taken out, so that's essentially 1. I won't write it. Well, maybe I will. Just to be thorough, I'm left with the k squared and a 1. And over here, I'm left with a 4, and I'm left with a k plus 1, because we took 2 essentially out of that sum, or yeah, that product rather. All right, so we have k squared times 1 plus 4 times k plus 1. So let's continue. K plus 1 squared divided by 4. And let's distribute the k to the 1 and the 4 through this binomial. So we're left with k squared plus 4k plus 4. Now, we could factor this. If you remember your factorization rules, if I have a quadratic, I'm going to try to factor this into 2 binomials. So here I need 2 numbers that multiply, that give me 2, but when I add them also give me 2, or 4. Sorry, multiply give me 4, then when I add them give me 4. So 2 and 2 is a great candidate. And if we FOIL this real quick, we can see that we get k squared plus 2k plus 2k plus 4, which is k squared plus 4k plus 4. So that indeed is the factorization. Now I'm going to write it like this. I have k plus 1 squared over 4 times k plus 2 squared, because k plus 2 times k plus 2 is just k plus 2 squared. Let's multiply this through, which essentially is just combining into 1 fraction. So you notice we have k plus 1 squared times k plus 2 squared divided by 4. If I think of it more like this, then we have this rule. Let's say a over b times divided by c squared is the same as a squared, b squared, c squared. Well, again, this is an exponent rule. Check out my video on exponents. So that means we can write this guy, k plus 1 squared times k plus 2 squared divided by 2 squared as k plus 1 times k plus 2 divided by 2 quantity squared. And this is precisely the right-hand side that we wanted to show. So indeed, the sum of squares, but we've just shown that the sum of cubes, not squares, is indeed equal to n plus 1 divided by 2 squared. You put a little square to say you're done with the proof, QED, however you want to do it, but we are done. All right. Thank you for watching. Like and subscribe. Let me know if there's anything you'd like me to cover from any area of mathematics. Hope you have a great night.